Okay, moving on. So in this video, we will talk about the concept of deep nonlinear mixed effects models, what that entails exactly, which types of models fall under this umbrella, and in particular, we are interested in applications of this for pharmacometrics. So we've seen this Venn diagram a couple of times before, and we've discussed basically most of the corners of this. And what's left is really this intersection of many of these topics, which is what we call DeepNLME. So we've seen universal differential equations as being the hybrid of some neural network or machine learning or universal approximator and a dynamical system, where we may already have or know some terms in the dynamics, but then we also want to use a universal approximator to fit or identify the missing terms in the dynamical system. And then we've seen, or we're kind of familiar with PKPD in general, which is sort of an application of nonlinear mixed effects modeling when combined with dynamical systems. So we can describe our PK dynamics, our PD dynamics, and then the parameters of those dynamics can be essentially the composition of some typical values, which are population level parameters, and random effects or deviation from typical values, which are random effects that are subject specific. And that's the concept of NLME, or really combining NLME and dynamical systems. And then we've also seen a tutorial where we can combine the notion of nonlinear mixed effects models or random effects essentially, and just simple neural networks. We don't actually need to have a dynamical system at all. And you can use this to model things like disease progression or any kind of, so you can still have the notion of time, I guess, but you don't have an ODE. But even without having the notion of time, you can just model or use neural networks directly with input random effects. And this is often called mixed effects neural network or neural networks. Now, DeepNLME is sort of what we call, or whenever we mix nonlinear mixed effects models with any notion of random effects, sometimes with dynamics, but also sometimes without dynamics, we often call this DeepNLME. So it's sort of this loose umbrella term, but really when two of the key use cases of DeepNLME that we found to be quite useful time and time again in the DeepPumas group are represented or summarized in this one slide here. The first is in missing dynamics identification. So if I know most of my dynamics, but then part of my dynamics is not well identified, I can model that with a neural network. Now, the key aspect of DeepNLME is I can actually have random effects in here as well. So the random effects can be used to define the other parameters, but they can also be used to or as input to the neural network. And so I can directly input some random effects to the neural network, so I can individualize or customize the output of the neural network for each individual. So if you think of the main individualized quantities or individual quantities, we have the covariates like age and weight and so on, but then we also have the random effects. And so random effects essentially represent this notion of unobserved covariates, or some individual degrees of freedom that the model is able to use to individualize or customize the output of that model for each individual. So you can think more generally of them as just individual degrees of freedom or individual parameters. And so being able to input random effects to the neural network gives us the ability to not just learn the missing dynamics term, but also individualize it, learn an individual dynamics for each, or a separate dynamics for each individual. However, those separate dynamics functions or those separate functions, they're still largely tied together. They're still largely, they share many of the parameters, because the actual parameters of the neural network are all shared between all the subjects. So you share the majority of the structure, but you still have some 1, 2, maybe 3 or more degrees of freedom that you can customize to get slightly different behaviors for different individuals, which allows us to model population data pretty well. And that's one primary use case that tends to fall under this DeepNLME umbrella. Now, the second use case is covariate modeling, where we have a neural network here that tries to capture either the entire covariate model or part of it. So maybe I already know how age affects absorption, how weight affects the volume of distribution, but I don't know how the rest of my covariates affect all these parameters. And so maybe I have some image data or some CT scans or any kind of rich covariates that I don't really have an easy, intuitive way to guess or to come up with a relationship between these covariates and my individual parameters, right? So these could be also omics data and any kind of rich wearable device data, etc. And the idea is we can use a neural network to actually enhance our covariate model, or to build the entire covariate model, such that we can take input covariates and then output these parameters of the dynamical system. Now we could have also input the covariates here directly as well, if we want. And so really it's up to us how we want to utilize neural networks with nonlinear mixed effects models. And you can even use it just to customize. So another sort of niche use case of neural networks is to learn a different distribution of the random effects using the concept of normalizing flows. And there is a talk about this on our YouTube channel. So there are multiple other use cases, but those two are perhaps the most useful that we found doing quite a few projects using DeepPumas. And you will see an exercise like this in the tutorial, but this is just to give you a notion that like when we were trying to test these DeepNLME methodology, a lot of the times we were actually pleasantly surprised that the model is able to capture the underlying sort of, or at least approximate the truth. The truth here being the actual model that was used to generate the data. So we would run many of these synthetic data studies where we use a model to generate some synthetic data. So the black points here would be the synthetic data points. And then we would try to fit a DeepNLME model to that by hiding some parts of the model and replacing them with a neural network. And then we maximize the marginal likelihood and we fit, or we visualize the results. And more often than not, we would actually be able to pretty well and pretty accurately approximate not just the population prediction, but also the individual predictions, and actually closely match what the underlying true model actually does. Now, this doesn't mean that the model we found is the true model, but the model we found seems to be a pretty good approximation of the true model, at least within the range of values that we have observations for. Now, how the model performs on unseen data, depending on how much structure you build into it. And that's also one of the exercises that you've already perhaps seen, but you will also see in the context of DeepNLME. If you build more structure into the model, often you can improve the extrapolation performance of that model to unseen dose levels and unseen territories like covariates as well. And so the DeepNLME methodology really allows us to customize how much knowledge we want to build into our model, but also use random effects to individualize the models. And then it seems like in many cases we're actually able to well approximate the underlying true model despite not knowing what that model is, or at least the DeepNLME is not aware of that model when we're fitting it. So again, revisiting this slide, we've seen this way at the beginning of the training, but the idea of a neural network in DeepNLME is just to think of it as a function, think of it as a sort of a local information processing unit, or in other words, a function that has some parameters. So the weights of the neural network are the population parameters, but then the inputs can be anything we want it to be. So it can be covariates, it can be dynamic variables, like if it's in a universal differential equation, it can be random effects. If we want to individualize the output of the neural network, we can even have time or the dose amount or anything we want as an input. And it's up to us to get creative with what inputs actually make sense and in different applications. And so if we're trying to learn the distribution of the random effects, then maybe just having the random effect as an input and then some transformed random effect as the output is what we need. And that's sufficient to maybe learn a complicated distribution of the random effects. If we're trying to learn a universal differential equation, then maybe we want the dynamics variables as input, maybe some random effects, maybe also time, but not necessarily. And that gives us the rate of change that we can use, or at least part of a component of the rate of change that we can use in a dynamical system. And so on. If I'm building a covariate model, I can have covariates as inputs, and then the output could be just added to the model in some ways. Or I can have covariates as an input even if I'm doing a universal differential equation. And so it's up to me to decide what I want this to be, those inputs here. And so one special case where we found also quite good results with using DeepNLME is if the input is a rich covariate, like an image. So think of the pixels of an image or some embedding model. Like you take the image, you pass it through an embedding model, you get some features extracted, and then you pass the features here to a neural network, and then the output is the parameter contribution, so the contribution to a PK parameter or PD parameter of interest. That's one interesting application. Now another is if I have perhaps some disease progression model or some sort of PK model, let's say, and then I'm interested in modeling disease progression, which is modeled using the pain score or represented in the pain score. But there's no easy mechanistic way to go from let's say the PK to the pain score, and so I can use a neural network to try and learn this PK-PD behavior or the effect of essentially the drug on the actual pain score that the patient reports. And this could be individualizable because every individual might have different pain tolerance, might have different pain thresholds, and different ways of reporting pain. And so we could use the random effect here to individualize this function so that we are able to fit the data that the patient gives us, essentially, or that the patient reports. And this would be an application of neural networks in this part of the model here. So in this part, we would have the central or the PK coming out of the dynamics, and then we can transform this in some way using a neural network and some input random effects before we actually use it to model the outcome. So the outcome would be the pain score. And so that's another application of neural networks that's not even covered in this slide here. And then we can obviously have the more standard universal differential equation where we have dynamical variables and random effects as inputs, and then some individualizable dynamic term or dynamics term. That would be this part here. So this application of neural networks is the one we're talking about. And then this here is, for example, we could input some time after dose or just time and some random effects, and then output some longitudinal biomarker or disease progression curve. So this would be, if you're modeling disease progression just as a function of time, there is no differential equation, but there's just time as an input and some random effects to individualize the disease progression curve, or to model some longitudinal biomarker, again, for which we don't really have a mechanistic model, and perhaps we don't really care about modeling the rate of change or having smoothness properties from the neural ODE, so we can just directly model this as a neural network function of time and essentially bypass the whole dynamics block here and just directly model this as a neural network function of time and some random effects. So you can see that there are many creative options to use a neural network in the context of DeepNLME, where the output could be perhaps added to a random effect, or the input could be a random effect and combined with different other inputs. And you can get really creative with these different model structures. And they each solve a specific problem or a different problem from the rest. But they all sort of fall under the umbrella of deep learning or neural networks plus nonlinear mixed effects models. Now, in the next few slides, I'm going to focus on a specific application of DeepNLME, which is actually the one we talked about here. So it's in covariate modeling, or like, let's say the input is just a whole bunch of covariates. It does not have to be an image, but can also be the actual RGBA values of the pixels of an image. But think of this as just some rich covariates here that we're interested in exploiting or taking advantage of, such that we are able to improve the performance of the model. So we want to predict the individual parameters here, like Ka and clearance and volume, etc. Or if you have some other random effects, you could even have random effects that are associated with the neural network that are then also predicted from the covariates. You could try to predict the contribution of the covariates, or like a contribution term that's coming from the covariates to predict the random effect that's then fed into a neural network. So you can sort of stack these models on top of one another, or stack these neural networks on top of one another. And so we're going to focus mostly on this part here, or this particular application, which is what's often called covariate identification using neural networks, or baseline covariate modeling, because we focus mostly on baseline covariates in this use case. So let's perhaps revisit what a classical nonlinear mixed effects model looks like. So this here is Again, we've seen this schematic before of a nonlinear mixed effects model or a hierarchical nonlinear mixed effects model with 3 subjects. And so we have the population parameters theta, we have the random effect for each individual, we have the covariates for each individual, and we have the response for each individual. And that's how you would write a model like this in DeepPumas. So that's a standard nonlinear mixed effects model with pre-existing covariates. Now, one way to actually figure out the covariate model, let's say we don't know what this covariate model is or what some of this covariate model is, so you can still leave some covariates in there, but let's say most of this is actually unknown. So we don't know this relationship here. And so let's assume we don't know that, and let's just drop it from the model. Now again, this doesn't have to drop every covariate. We could bake in some covariate model, but let's just for simplicity assume that we dropped all of them. And in this case, the model looks something like this. And this here again is an NLME model just without the covariates. And so we assume that all of the individual variability, so all the between subject variability that was explained previously either through the random effects or through the covariates, now we assume that all of this is coming from the random effects. And so if we go back here, what that means is essentially just assuming that this entire part here, like this covariate model and this covariate model, they don't exist, and just replace both of these with a random effect, right? Just assume that actually we already have a random effect here, but we can assume that all of the variability is captured by this random effect. Or we can replace these by a separate random effect that we assume, because let's say this is multiplicative and this is additive. There are identifiability issues here, but that's just a dummy example. But we can assume that the entire variability between subject variability is not really captured by the covariates anymore, but is actually captured by just the random effects in the model. And that's what this model structure here looks like. And actually some of the example NLME universal differential equations that you will see in the tutorial. So we often start, for example, with a universal differential equation that has random effects in it, and then doesn't have covariates yet. So let's say we are trying to build this model here, or trying to, let's go back to this model. Let's say we're trying to figure out or build this model from scratch. So one way to do this is to not have any covariates initially. And let's say we don't even know anything about the dynamics, and so we can have, or we don't know parts of the dynamics. So we can have a universal differential equation here, or some neural ODE, with some input random effects. So these random effects could be used on the sort of parameters that have a meaning, or the parameters that we encoded directly in the model, the PK parameters that we assign or we defined in the model ourselves. Or we could have random effects also as input to the neural network, which have less meaning, but they just mean more generally degrees of freedom in the model. And so we can start with a universal differential equation that has random effects, but no covariates. And then we can build a covariate model after that. So after we fit this nonlinear mixed effects model by maximizing the marginal likelihood and figuring out good values for those population parameters, good values for the omegas, good values for the weights of the neural network, we can then go back and try to actually figure out what's a good covariate model. So your dynamics or your model without covariates could either be a model that includes a neural network, or it doesn't have to be as well. So you could also just have a regular PKPD model just without any covariates, right? So this sort of covariate model identification is completely orthogonal to whether your dynamical system has a neural network or not. It may or may not have a neural network, but the same methodology applies. Now, the challenge with this model is that it does not have covariates, and therefore it cannot exploit those covariates, those baseline covariates, to give better predictions at baseline. Now, the value of covariates is that they allow us to make better predictions at baseline without observing anything yet. Now, once we observe some values, we can use that to actually get the empirical Bayes estimates and then also improve the prediction and the fit of the model. But without observing any observations or any measurements for Y for a specific individual, often the best or the only information we have to go on for that particular individual are the actual covariates of that person. And some of those covariates could be, again, implicit, like the dose amount. Those are implicit covariates, or time, and so on. But here we're talking more about the explicit sort of baseline covariates, like the weight and the age and the sex and any kind of measurement or any kind of image or scan that we can get observations for. for that patient at baseline. And so in absence of any observed response data, if we don't observe any Ys yet or any part of Y, the best prediction is going to be independent of the individual under consideration. What that means is because we don't have any other covariates, so let's say the same input dose is given for all of the patients, which is sort of the only implicit covariate if you have a PK model, then because we don't have any covariates and we don't have any individual observations, the best population prediction will be the exact same for all the individuals. So we won't be able to make any difference or make any different prediction for individual 1 versus individual 2 versus individual 3 because we don't have baseline covariates. Right. And so that's far from ideal. We don't want that. We want our model to be customizable. Even at baseline, we want to be able to make individual predictions that are accurate for each person. And that's something that's not possible if we don't take advantage of these baseline covariates. And so the idea is that we want to then find a function mapping or a function that maps the covariates to the random effects of the universal differential equation, but it doesn't have to be, again, a sort of use a neural network. It could just be a standard PK/PD model. But let's say we want to find a mapping between the covariates and these random effects here that best fit the data. And so we fit the model first, we find the empirical Bayes estimates, and then we're trying to see how much of this empirical Bayes estimate is actually predictable or can be identified from the covariates directly. So let's say for subject 1, the best fit or the best value of eta that fits the data here is eta 1 equals 1. And for the subject, it's eta 2 equals 0. And for the subject, it's eta 3 equals minus 1. And so each individual will have their own sort of empirical Bayes estimate or their own best value of the random effects. Now, the idea here is to say, okay, what if we can find a model that takes as input the covariates and then is able to perfectly predict that this eta 1 here, given the covariates of this individual, given the x of this individual, this output of the predictive model that we have is eta 1 equals 1 or eta equals 1. And then for the second subject, it's able to predict that eta equals 0. For the third subject, it's able to predict that eta equals minus 1. And so if you find the mapping that goes from the covariates to the empirical Bayes estimates or to the best values of the random effects that approximate or that fit the data here, that gives us the best individual prediction, if we're able to find such a mapping, then that means we're able to get the same quality, the same quality as the individual prediction, having seen all of the observations at baseline. So at baseline, before observing anything, we're able to perfectly predict what the value of eta 1 is that would actually perfectly match and fit all the observations from that individual. And that means we're able to get the same quality as the IPRED, the same quality of prediction as the IPRED, but at baseline without observing anything yet. And that's quite powerful. And that's what we're trying, that's sort of the ideal goal that we're trying to get to, is being able to approximate the empirical Bayes estimates as closely as possible from the covariates, because if we're able to do that, then that's the best possible model for that subject. That the empirical Bayes estimate gives us the best possible individual model for that subject, and therefore, if we're able to get to that model at baseline, then that's sort of the best scenario that we are trying to achieve. Now, the risk here is that we might overfit, we might underfit, we might not be able to predict those empirical Bayes estimates very well, and there's a lot of sort of like a lot of tricks that need to go into trying to make sure we actually find a good model. But what that looks like in a schematic is something like this, where we have the empirical Bayes estimates coming from the fitting of this covariate-free model. So we first fit this model using the marginal likelihood, maximizing the marginal likelihood, and then we get the empirical Bayes estimates using the formulas that we've seen in the previous video. And then we try to fit the empirical Bayes estimates from the covariates. So the target here, the output, is the empirical Bayes estimates, and the inputs are the individual covariates. And then we have some machine learning model, which doesn't necessarily have to be a neural network. It could be an XGBoost model, it could be a random forest, it could be any kind of model that we want. And this here is actually just a very classical supervised machine learning problem. And so we have some input variables, we have some output variables. So having computed these from the previous stage here, from the previous step here, Now that we computed those, we can just fix them, and they become just number outputs, or maybe we have 3, 4 random effects for each individual. So that would be a vector of length 3 for each person. And that's just, again, a function that's trying to map some inputs x to some outputs eta. For individual 1, it's x1 and eta 1. Individual 2, it's x2 and eta 2. And individual 3, it's x3 to eta 3. And the idea is we want to find this mapping here. And this mapping can be sort of encoded in a machine learning model. And then the whole task is often called supervised machine learning, or a regression problem. This is often called a regression problem as well. Now, if we're able to find the model, a machine learning model that's actually perfectly able to predict the random effects or the empirical Bayes estimates given the entire observation. So these empirical Bayes estimates are computed from the entire observations, or all of the observations y. So if we have 10 observations for each individual, then we're using all the 10 observations to get the best value of eta that fits these 10 observations. And then this value of eta here is exactly the output of the machine learning, or the target output of the machine learning that we're trying to predict as accurately as possible. Now, the idea is that if the information in the covariates are sufficient to predict or to figure out exactly what those values of the random effects are. So let's say this random effect is clearance, some random effect on clearance, random effect on weight, random effect on the volume. Random effect on clearance, volume, or absorption. And some of the inputs here could be age, weight, etc. And let's say the information in these inputs are actually sufficient to figure out what the specific values of eta should be, then our machine learning model should be able to predict those empirical Bayes estimates from the covariates. And once it's able to do that, we should be able to use it inside the model, or embed it in the model, or augment our model with this machine learning component, such that at baseline, before observing any values, we're actually able to get a perfect prediction. We're able to get the best possible prediction even at baseline, and not having to wait to see all the observations for that individual. Now, the hope is that this kind of mapping can be generalized to other subjects that have not been seen before, because those subjects, we already have the data, so we can just get the empirical Bayes estimates if we want to, and get the I-prints. But the idea is that for other subjects that are unseen, that subjects that have not been collected yet, or data have not been collected for them yet, we are able to make such a prediction, and then we're able to generalize this model such that we get the best possible prediction for those subjects as well, even before we actually observe any data for them. And so a new patient walks in through the door in a clinic, you're able to use this model to make perhaps individualized recommendations for dose, or individualized treatment recommendations, because the model is giving you this ability to accurately predict how the response is going to be, perhaps for different dose levels. Now, one important thing to keep in mind is that any covariate model that we build here in this approach, or using this approach, does not necessarily have to be causal in a way. And so this is just an associative model, and the idea is that just because X is predictive of some of these quantities here, so if I'm able to predict, for example, absorption and clearance and volume from some rich covariates, this does not mean that changing these input covariates will change these output quantities here. And so you can use this for decision making as long as the decision is not actually changing one of those input covariates. Perhaps you can change the dose, which is not input to this neural network, and is just part of central here. And that might still give you, like, the covariate model might still help enhance the prediction for that kind of intervention, and then you're able to actually predict the response more accurately for different dose levels, because the dose level was not directly, let's say, input or considered in this model. And so your decision making can be sort of external to the model, but not necessarily changing one of the inputs. Or you should not think that if I change one of those inputs, my model will, or the output will change in that way, because that's more of a causal sort of effect, or that would be the case if your model was causally correct. But here the model is just using or learning mappings or predictive relationships that are more associational in nature. So it's important to keep in mind that just because X1 is predictive of clearance, or some specific covariate is predictive of clearance, doesn't necessarily mean that this covariate, actually changing it, will change clearance, right? It could just be that there is maybe a common cause or some other kind of reason for that association between the inputs and the outputs. So it's good to keep that in mind, that when you interpret and there are ways to, for example, once you fit a machine learning model, you can use explainability techniques like SHAP values to try and figure out exactly which inputs are used to predict which outputs. But it's important to keep in mind that those relationships don't have to be causal. They might be in some cases, but that would have to be tested separately. And the neural network or the machine learning does not give you that guarantee, and you need to be careful when interpreting this. The results of this covariate modeling. And so perhaps if you find that a specific covariate is predictive of a specific quantity, but it doesn't make sense from a medical point of view, you can maybe look at all the other covariates that might be correlated with this covariate. And maybe one of them is actually medically significant, or it makes sense that it would have a causal relationship on a specific parameter. And so it's important to second or to double check the output of the supervised machine learning here, or the covariate identification, if your goal is to actually interpret this covariate model and perhaps use it to make any interventional decision making or counterfactuals, like what if I change the weight of the individual, what would have happened in the response. So things like that require that your model actually is causally correct. So just a caution, but mathematically, again, we're just fitting the inputs are a bunch of covariates. Could be image data, could be scan data, could be very rich baseline biomarker data, could be anything that we just don't know how to use exactly in the model, and the output is a bunch of empirical Bayes estimates or random effects from this baseline model. So let's call this the baseline model, or the base model, the reference model. And in this extreme case, we don't have any covariates, but you could also have some covariates if you know exactly how to use those covariates. And then the covariate identification can be used for all the other covariates that we don't know how to use. Now, after we fit this supervised machine learning model, we do a step which is what we call here augmenting the model, or the augment step. And this whole workflow, you will find that we refer to it in the DeepPumas group as the augment workflow for this reason here. And so using the machine learning model, using the input covariates for each individual, or the baseline covariates for each individual, we can come up with a prediction for the random effects. So we try to predict the random effects for subject 1, we predict the random effects for subject 2, we predict the random effects for subject 3. Now each of those could be a vector of length 3, 4, 5, however many random effects we have in the model for that specific individual. And we take this prediction of the random effect, and keep in mind that this prediction may not be perfect. So we may have some residual variability, some of the variability in the random effects here, or some of the random effects response or the output in the supervised learning may not have been easily fitted, or the machine learning may not be perfect, either because the machine learning model is perhaps underfitted, or because there's not enough information in the covariates to actually fit precisely or perfectly fit and figure out what the empirical Bayes estimate should be. And so if the covariates here don't carry enough information, you expect your model to not be perfect. And in such a case, we actually have some residual between subject variability. So we have some additional between subject variability between the different etas that was not explainable by the covariates. We could not use the covariates to predict that amount of variability. And so we still need those random effects here, but now we use those random effects, assuming it's a Gaussian, for example, we use those random effects in an additive way. So we add the random effect here to the prediction of the machine learning model. We add this random effect to the prediction of the machine learning model for the second subject, and same thing for the third subject. And so we do this additive step here, where you can think of this now not as the entire between subject variability. Before, it was sort of the entirety of the random effect explains all of the between subject variability. Now the random effect only explains the residual between subject variability that's not explainable by the covariates. So anything that's explainable by the covariates, we'll be able to go through this prediction here, and then we don't really need, let's say for a specific subject, we got perfect prediction. So for that subject, maybe we don't need eta 1. And so the empirical Bayes estimate of eta 1 for this subject would be 0, because we don't really need it anymore for this subject. We were actually able to perfectly get the perfect IPRES, the perfect prediction just from the covariates, right? So the covariates for the subject were perfectly informative, and we don't need any more correction. But for other subjects, we might not be getting perfect prediction. And so we might need some additional between subject variability or some additional random effect to actually capture this additional variability that was not easily captured or was not possible to capture by the covariates. Right? And so the meaning of the random effect now changed. It's no longer the entire between subject variability, it's just the residual between subject variability that it actually represents. And so what this means is actually the omega or the covariance or the variance of these etas now have to change, or the distribution of those etas may be different from before. So if we had, let's say, the omega of those random effects was 5 previously before to fitting the covariate model, after fitting the covariate model, that might drop to 1 or 0.1 because now we explained most of the omega or most of the variance of the between subject variability or the variation in the individual parameters. Most of that has been explained by the covariates, but some of it is still not perfectly explained. And so you'll notice that there is going to be some reduction in the amount of between subject variability that you get after you augment the model with your covariate model. And this is just a nonlinear mixed effects model at the end of the day. It has some population parameters, it has some input covariates, it goes through this complicated machine learning stuff, but then at the end of the day, it's just an NLME model. It's just a model that has population parameters and the machine learning itself, if it's a neural network, then there's just more population level parameters. And so the parameters of the neural network would be just additional population level parameters. Or you can freeze it. So you can also freeze this and just think of it as a constant or as a part of the structure of your model now. It's no longer like fittable, or you don't have to fit it, and that's more typical if you use like a random forest or some model that doesn't have easily trainable parameters with gradient descent or with gradient based optimization. Then you can just figure this out once and then freeze it, and then you don't need to change it. And more often than not, actually, we find that we don't really need to change this after we fit it in this step here. So once we figure out the machine learning, we can fix it, but you can also just fine tune it and think of the parameters of this, let's say, neural network as just more population level parameters. And so we have here just a few more population level parameters. We have the input covariates as before. We have the random effects as before. Their meaning changed. Now it's just the residual variability for the between subject variability of the individual parameters, but they're still random effects. And then we have the response, right? So the structure here at a high level is not very different from this kind of structure here, right? It's just a slight variation of this kind of structure here. So it's just a nonlinear mixed effects model anyways at the end. And that's what we often call the augmented model. And this here is a model that has, again, the covariates have already been embedded into the model. And all of this is just a few lines of code in DeepPumas, as you will see in one of the tutorials that you will be working on after this presentation. So let's summarize. So we should be able to fit an NLME model, or one way to do this covariate modeling or this workflow for covariate modeling. And by the way, this is not the only way to do covariate modeling, but that's just a convenient workflow. When you have only baseline covariates, we can actually do this multi-step process, and then we end up identifying a model with these rich covariates actually being used. And we could have just we could have defined this model, for example, upfront at the beginning and just fitted the whole thing simultaneously by maximizing the marginal likelihood. So that would be another alternative. We don't actually need to do this multi-step process. You can just define one model, one big model here, and just fit the whole thing together. However, this tends to take a long time to fit, and so what we found to be more computationally efficient, and my colleague Nicholas actually developed this workflow, what he found to be more computationally efficient is to do this in multiple steps, where we first fit the model without covariates, then fit the covariate model, and then augment the two together. And this tends to achieve very similar results to fitting the whole model simultaneously, but much, much faster, so your efficiency is much higher. And so this particular workflow for finding covariate models involves a few steps. First, you fit an NLME model without covariates, or with only the covariates that you know how to use in the model. but without all the covariates you don't know how to use in the model. And the idea here is you want to describe the individual time courses and find the empirical Bayes estimates, or just find a good model that's able to capture the data or the distribution of your data and fit the individual courses, the time courses very well. But you don't really care about the covariate model yet. You just care about the structure of your dynamics. You care about putting the random effects in the right place. You care about getting good simulation performance, getting good IPREDs, right? So you care about more of these characteristics of your model, not yet the covariate part of the model. Then the second step would be to extract an approximation of the posterior distribution of the random effects. Now, so far I've been talking about just using the empirical Bayes estimate. The empirical Bayes estimate is just the mode of that posterior. So you can think of it as just a point approximation of the posterior, but we can also use actually a whole distribution approximation of the posterior, like a Gaussian approximation of the posterior, and then sample from that. Or we can use MCMC approximation of the posterior of the random effects and then sample from that. And so the target here does not just have to be the empirical Bayes estimate, it could also be samples from the posterior in general. And ideally that's what we want to do, is to have actually take the uncertainty of the random effects into account and also sample from the posterior distribution here and not just use the empirical Bayes estimate, although in the most common workflow that a lot of papers do, you'll find people just use the empirical Bayes estimate. Now in DeepPumas, we do something similar to actually sampling from the posterior by using some weighting schemes in the supervised learning routine. But even without the weighting, you could think of the empirical Bayes estimate as just a point approximation of the posterior, and you often get pretty good results even with just that. But more generally, we're extracting an approximation of the posterior. Could be the empirical Bayes estimate, could be a Gaussian approximation, could be some MCMC samples. And then the third step is to fit a machine learning model with inputs as the baseline covariates, and the output is the approximation to the posterior. So think again empirical Bayes estimate or some approximation of the posterior or some samples from the posterior. And that's the step that we talked about here. This step here, where we have input covariates and the output is the random effects or the empirical Bayes estimates. And we try to fit a supervised machine learning model to learn this relationship here. And then finally, the last step, we augment the original nonlinear mixed effects model with the machine learning prediction. And that's this step here. And in the most popular workflow that we have, we just do this additive augmentation, essentially, where we take the output of the neural network and then we add to it some residual random effect and often apply some transformation as well to respect the domain of the random effect. And then we use that we use it in the model in the same way that we would actually use the previous random effects. That's an important point, maybe I forgot to mention, is that the outcome here, the output of this plus, is used in exactly the same position in the model as we use the original random effect. So let's go back maybe to an example here. So let's say we have the original random effect being this eta I2. And so the output of the plus, the output of the augmentation of the machine learning plus the new random effect would be used exactly in this position here, right? So it'd be used instead of this, we would just replace this with, let's say, the new eta I2, which is, again, just the residual variability plus the output of the neural network, and it would be used to replace this here. And then the rest of the model structure is the same. So CL is still theta2 times the exponential of this new function here plus the residual random effect, right? And so when we look at this figure here, the way to think about it is that once we add these two, and then this arrow here represents the exact same relationship that Y2 used to have on eta2. So previously in the model, Y1 used to depend on eta1, Y2 used to depend on eta2, and Y3 used to depend on eta3, actually in this model here as well. And so this arrow here now is going to be the exact same relationship as the relationship between Y1 and the sum of eta1 and the output of the neural network. So this arrow represents the exact same relationship as this arrow. And this arrow represents the exact same relationship, the functional relationship, as this arrow here, right? So once we add the output of the neural network to this residual random effect, then we use the output in the exact same position, the exact same way as the original random effect in the covariate free model. So that's very important to keep in mind. And that's the last step. And then once you have this here, you basically have another nonlinear mixed effects model. And the nice thing about this is you can do a visual predictive check. You can do residual analysis. You can do individual prediction versus observation. You can do all your standard diagnostics based on this model here, because it's just a nonlinear mixed effects model. And the way it's implemented in DeepPumas is very clean, because you only use a few lines of code to do all of these different steps here. And then you end up with another object that's just another fitted Pumas model, basically, that you can use anywhere you would use a normal Pumas model or a normal fitted Pumas model. And so you can use it again to compute diagnostics, to do all sorts of plots, etc. And so it's very nice and systematic in the way it's implemented in DeepPumas, and you will get to play around with this in one of the tutorials. And with this, this is the last presentation in the DeepPumas onboarding, in the introduction to DeepPumas learning path. And so I hope you learned a lot in this, or you learned something at least in this onboarding, and you will be going through a couple more tutorials after this presentation, and then we might introduce more learning paths in the future as well. And then of course there are the office hours, so hopefully this was useful, and maybe after you actually gone through the exercises, you will probably appreciate how easy it is to do this. It may seem like it's a complicated thing to do, but it's actually quite straightforward the way it's implemented. It's straightforward to use, and I hope you have a good time using DeepPumas in general. So thank you.